on the deep dive.
Okay, let's just dive right in. What happens when the sun decides to throw a punch? And I don't mean just a little jab. I'm talking a full-on solar haymaker aimed directly at Earth.
It's really the ultimate collision, isn't it? It's where just the overwhelming, terrifying beauty of the cosmos clashes violently and completely unexpectedly with the fragile infrastructure we've built.
And that's exactly what we're talking about today. We are doing a deep dive into the benchmark for all solar catastrophes, the Carrington Event of 1859.
And it is quite the benchmark. This is, to this day, the most intense geomagnetic storm in recorded history.
Right. It all went down on September 1st and 2nd, 1859, during what astronomers call solar cycle 10. And the intensity was, it wasn't just causing a few glitches.
No, it was literally igniting fires in telegraph stations.
That's the part that always gets me. Fires.
And that contrast is really the key to this whole deep dive.
Yeah.
Because back in 1859, the technological impact was, it was localized. It was confined to a very new, very basic telegraph system.
A few sparks, a few melted wires. A big deal for them, I'm sure, but ultimately fixable.
Exactly. A repairable crisis. But if an event of that same magnitude were to happen today, the consequences would just balloon. It would go from a localized problem to a multi-trillion-dollar global systemic crisis almost overnight.
Okay, so that sets our mission for this deep dive perfectly. We're going to jump into the source material you brought and really unpack 3 critical things about this solar monster.
First, we have to look at the specific historical moment of its discovery, the stunning immediate impacts. Auroras that wrap the entire world in light and the chaos it caused for the new telegraph lines.
Then second, we need to get into the physics, the surprising and frankly terrifying reason why the storm was so unbelievably fast and so violent. It completely changes how much warning time we might have.
And finally, we have to confront the modern threat, the really high-stakes financial and societal projections. We'll look at why a Carrington-class event today isn't just a threat to power grids, but to everything, even our food supply.
So 1859 wasn't just some historical curiosity.
Not at all. It was a warning shot. It was the moment the sun almost ended the world as they knew it.
Okay, so let's start at the very beginning. The moment of discovery. Because this didn't just set a benchmark for intensity, it fundamentally changed how we view the sun-Earth connection.
Before 1859, mainstream science really just saw the sun as a predictable source of light and heat. A constant. The idea that a sudden visual event happening 93 million miles away could instantly affect instruments here on the ground.
That was fringe theory, right?
Borderline. It was speculative, to say the least.
And then on September 1st, 1859, 2 British astronomers working completely independently, they gave us the first hard evidence that the sun was way more volatile than we thought.
Yes, Richard Carrington and Richard Hodgson. And the story around Carrington's observation is just legendary. He was at his private observatory sketching this very large, very complex group of sunspots.
Sunspots being those cooler, darker, magnetically active spots on the surface?
Exactly. And just before noon, he sees it. An intensely bright, just a blinding white light erupting right near that sunspot group.
The visual signature of a massive explosion, what we'd now call a solar flare.
Precisely. And we have his sketches. They actually document this bright event moving across the sunspot group. He labeled it moving from positions A and B to C and D within about 5 minutes. Then it just vanished.
So that's the moment the energy is released, the fuse is lit.
That's the moment. And that flare hurled a massive bubble of plasma and magnetic field, what we call a coronal mass ejection, or a CME, directly toward Earth.
But the connection, that cause and effect, wasn't immediately obvious, was it, even to him?
Well, here's where it gets really interesting. At the exact same time Carrington saw the flare, a Scottish physicist named Balfour Stewart was at the Kew Observatory near London, and he was recording Earth's magnetic field.
With a magnetometer.
Right. And at that exact moment, his instrument recorded a tiny but distinct, sharp little jump in the magnetic record.
The so-called magnetic crochet.
That's it. That tiny little wiggle was the first piece of hard evidence. The light and radiation from the flare arrived in just minutes, hit our atmosphere, and caused a subtle jolt in Earth's magnetic field. It was like the universe providing proof of concept.
Incredible. One event, Two completely different observations, one visual, one magnetic happening at the same time.
But they were cautious scientists. Carrington suspected this flare was the cause of the monster geomagnetic storm that arrived the next day, but he was very reserved about it.
Right, he used that famous phrase, one swallow does not make a summer.
He did? He knew he needed more than a single coincidence, no matter how compelling it was.
So who was it that finally connected all the dots?
That would be the American mathematician Elias Loomis. He did the really painstaking work of compiling reports from all over the world, magnetic disturbances, telegraph failures, and of course those incredible auroral displays.
And he cross-referenced everything against Carrington's timing.
He did. And his work really solidified that solar-terrestrial connection. It's foundational to our modern understanding of space weather.
Okay, so the flare is seen on September 1st. The massive particle storm, the full punch, arrives and peaks on the 2nd. This brings us to the speed of the thing, which is where this shifts from a cool historical event to a terrifying modern threat.
Absolutely. The speed is the single most critical factor here.
Yeah.
A CME is this huge bubble of solar plasma and magnetic fields, and it gets ejected at millions of miles per hour.
And how long does that 150 million kilometer journey usually take?
Typically several days, 3, maybe 5 days to reach Earth. That's the transit time our current forecasting models are based on.
Because it's pushing through all the other stuff out there, the ambient solar wind.
Right, that solar wind plasma acts like a kind of cosmic drag. It slows it down.
Yet the Carrington CME, it didn't play by those rules.
Not even close. The record shows it made that entire 93 million mile journey in a mere 17.6 hours.
Less than a day. That is horrifyingly fast. If we only get 17 hours of warning today, that basically collapses any window we have for mitigation. So how? How was it so fast?
The leading theory is what we call the clearing the way hypothesis. It suggests that the path was essentially cleared for it by an earlier solar event.
Like a cosmic snowplow came through first.
That's a perfect analogy.
Wow.
We know there was another earlier solar eruption a few days before. It's likely the one that caused a big aurora event on August 29th. That first CME traveled out, and it swept away most of that ambient solar wind plasma, that cosmic friction, along the path to Earth.
So the space right in front of the main event was basically a vacuum.
A much less dense medium, exactly. So when the real monster, the Carrington CME, launched on September 1st, it hit significantly less drag. It was able to maintain this incredibly high velocity the whole way here. It just served a cleared lane right to our doorstep.
And you see the force of that impact in the magnetic data in something called the Drest index. The source material said it was between over 0.80 and 1.75 microteslas. Can you put that number in context for us?
Right, so the Drake, or Disturbance Storm Time Index, it measures the severity of a geomagnetic storm. A normal day is around 0. When a big CME hits, it compresses our magnetic field, and the Drake number goes negative.
So the more negative, the worse the storm.
Precisely. A severe storm today might drop to, say, minus 100 nanoteslas. The Carrington event was estimated to be as strong as minus 1750 nanoteslas.
It's just off the charts.
Completely off the charts. It's the physical proof that Earth's protective magnetic bubble was just violently compressed and completely overwhelmed. A monster hit us, and we only had about 17 hours to see it coming.
Which paints this picture of a planet just caught completely off guard by a perfectly timed solar attack. So now we move from the physics to the surreal and unforgettable impact it had right here on the ground. When that super-fast CME hit, Earth's magnetosphere basically screamed, and the sky put on a light show that has never been equaled since.
The historical records of the auroras from this event are just. They're the most evocative part of the story. And we have to use the word global in its truest sense here. The auroras, both the northern and southern lights, were seen way beyond their usual polar regions.
And this is the part to really emphasize. We're talking about places incredibly close to the equator, places that never, ever see the aurora.
Absolutely. The records show sightings in south central Mexico, Cuba, Hawaii. I mean, even as far south as Colombia, which is practically on the equator.
Can you imagine seeing the Arctic lights over the palm trees in Havana? It must have felt like the world was ending.
It wasn't just in the north either. In the south, you had the aurora australis seen all across Queensland in Australia, southern Japan, China, New Zealand. For anyone living in that equatorial band, it must have felt like a fundamental violation of the natural order of the sky.
And the light wasn't just geographically widespread, it was intensely bright. We have these amazing anecdotes that really paint a picture. The one about the Rocky Mountain gold miners is my favorite.
It's such a relatable example. They woke up in the middle of the night, saw the glow, and genuinely thought it was morning.
So they got up and started making breakfast.
They did. The reports say the glow over their camps was so bright, so pervasive, they mistook it for dawn. They started preparing meals, getting their gear ready for the day. That tells you the ambient light was brighter than a full moon.
And we see that confirmed back east, too. In the northeastern U.S., people could apparently read a newspaper just by the light of the aurora alone. This wasn't a faint shimmer.
No, it was a functioning, natural streetlight. The Baltimore newspaper report from September 3rd, 1859, gives this beautiful description. They said the light was more brilliant and the prismatic hues more varied and gorgeous.
Greens, reds, purples, a whole light show.
Yes, and they said it covered the whole firmament, apparently like a luminous cloud. But here's the key sensory detail for me. They said the light was greater than a full moon, but had an indescribable softness and delicacy.
So it wasn't harsh. It was this powerful but gentle luminous blanket that turned midnight into twilight.
Which must have been both wondrous and deeply unsettling. We also have this incredible account from an Australian gold miner, C.F. Herbert. He wrote about it 50 years later, in 1909.
50 years later. The fact he still remembered it so vividly tells you everything.
It does. He described looking out of his tent and seeing these streams of light of every imaginable color shooting up from the southern sky, all becoming a rich purple when they reached the top of the sky, the zenith. He called it a sight never to be forgotten.
And his account really captures that split reaction people had back then.
It does. He framed it as two groups. On one hand, you had the rationalists who saw nature in her most exquisite robes. They saw the science and the beauty in it.
And the other group?
The superstitious. For them, it brought dire forebodings. They thought it was a sign of Armageddon, the end of days. This wasn't just a physical event. It was a profound psychological one. The sky, the one thing that's supposed to be constant, was suddenly on fire.
It just shatters your perception of stability. Whether you see it through the lens of science or religion, it forces you to confront this immense, untamable power of the universe.
So while the auroras were this beautiful, apocalyptic spectacle, the real measure of the storm's power, and the real warning for us today, was the immediate failure of 19th century technology.
Which at the time was the telegraph system. This was the absolute cutting edge, the nervous system of early globalization. And when that CME hit, telegraphs across Europe and North America just failed instantly.
And they failed because of something called geomagnetically induced current, or GIC. This is the real villain of the story for us today.
Right. Can you break that down? How does it work?
When all that solar plasma slams into our magnetosphere, it creates these huge electrical currents way up in the atmosphere. Those currents then induce secondary currents on the ground, and those currents look for the easiest path to travel.
The path of least resistance, which would be long metal conductors like power lines.
Or telegraph lines, or, and this is a key detail, even oil and gas pipelines.
Wait, pipelines too? How does that work?
Well, the Earth itself isn't a great conductor, but a long metal pipe is an excellent one. So that current can flow along the pipeline, and where it enters or exits the pipe, it can accelerate corrosion, potentially leading to breaches. It adds a whole other layer to the potential disaster.
Wow. Okay, so for the telegraphs in 1859, this GIC just completely overwhelmed their systems.
It flooded them. The accounts are dramatic. Operators reported getting painful electric shocks right from their telegraph keys. People saw sparks literally flying off the wooden telegraph pylons.
And even off the paper tape as messages were being printed. That's an incredible image, the whole system just spontaneously combusting.
It is. But inside all that chaos, we have one of the most amazing moments of scientific discovery in real time, the famous batteryless conversation.
This is the aha moment. So on the line between Boston and Portland, Maine, the operators figured something out.
They realized the induced current, the GIC, was so powerful they could actually use it. They managed to keep talking to each other without using their batteries at all. They were running purely on the aurora.
And we have the transcript of their conversation. The Boston operator basically says to the Portland operator, hey, cut your battery off.
And he does. And then Boston confirms, mine is disconnected and we are working with the auroral current. How do you receive my writing? They were powered by the solar storm itself?
The reply from Portland is amazing. Better than with our batteries on.
Better. He says the current comes and goes gradually, but it's a stronger, cleaner signal. They kept this up for 2 hours, transmitting messages using only the raw electricity generated by a solar storm 93 million miles away.
So by taking their own batteries offline, the signal actually got better.
It did. The Boston operator figured it out in real time. He noted the auroral current seemed to neutralize and augment our batteries alternately. Basically, their own power source was getting in the way of this much more powerful natural current.
It was the first time they'd ever transmitted more than a word or two that way. They accidentally tapped into a cosmic power plant.
And it was a huge lesson. In 1859, GIC was a novelty, a source of sparks. Today, that exact same phenomenon applied to our massive modern power grid is an existential risk.
Which brings us right to the modern threat. We have to contrast the limited damage of 1859 with the potential for absolute devastation a recurrence would cause today.
The difference is complexity and interdependence. In 1859, the telegraph going down was an inconvenience. Today, our entire civilization runs on electricity. Hospitals, finance, water treatment, the food supply. Everything depends on the grid.
So if a Carrington-class storm hits now, the GIC wouldn't just cause a few blackouts. It would flood the entire high-voltage distribution network. And the weakest link there are the big transformers.
Exactly. The high-voltage transformers. They're vulnerable because the GIC acts like a DC current being injected into an AC system. It pushes their magnetic cores into saturation. They start to heat up incredibly fast, and they can catastrophically fail. They can literally melt down.
And these are not something you can just go and replace easily.
Far from it. They're custom built, they weigh hundreds of tons, and it can take months, sometimes years, to manufacture and install a new one. A cascading failure of hundreds of these across a continent could mean blackouts that last for months, not days.
And we know this isn't just theory because we've had some very close calls. The closest was actually pretty recent, on July 23rd, 2012.
That 2012 event was, by every measure, a genuine Carrington-class storm. It had the flare, the high-velocity CME, the whole package. It was the same monster.
So why are we still here talking about it? Why didn't it hit us?
Pure, dumb orbital luck. The CME's trajectory missed Earth's orbit by about 9 days. If that eruption had happened just 9 days earlier, the Earth would have been right in the crosshairs.
We were spared by less than 2 weeks. That should be the single loudest wake-up call imaginable.
It should be. We've seen what even milder storms can do. The 1989 storm knocked out power to all of Quebec. And even in May 2024, those storms pushed auroras as far south as Puerto Rico, showing the system is still vulnerable.
So let's talk about the cost. Because when you try to put a dollar figure on a modern recurrence, the numbers just become astronomical.
They really do. The best estimate we have comes from a 2013 study by Lloyds of London and Atmospheric and Environmental Research. They tried to quantify the cost just to the United States.
Oh, well, what did they find?
The initial estimate was somewhere between $600 billion and $2.6 trillion. If you adjust that for inflation to 2024, you're looking at a range of about $794 billion up to $3.4 trillion.
Over $3 trillion for one country.
And that's not just replacing hardware. That figure represented up to 15.5% of the U.S. annual GDP at the time. A loss on that scale implies not just damage, but a long, crippling economic depression as all the dependent sectors fail.
But it's not just about the grid. The sources highlight this really surprising indirect effect on a sector most people would never connect to space weather: agriculture. This is the real why you should care moment.
This is a crucial insight. The problem isn't the sun hitting the crops, it's industrial dependency. Modern agriculture runs on manufactured inputs, fertilizers, pesticides, that kind of thing.
And those things are made in huge industrial plants that need a massive, steady supply of electricity from the grid.
Precisely. If that grid goes down for months, the factories that make fertilizer shut down. So farmers might have local power, but they can't get the inputs they need to actually grow the crops.
And what does that do to global food production?
The models that looked at this scenario are catastrophic. They projected global crop yields would fall by 38 to 48%.
Nearly half the world's food supply gone. Not because of a drought, but because of an electrical failure.
And in some places, like Central Europe, the projected losses were as high as 75%. This is the cold realization. A Carrington event isn't just a tech problem. It's potentially a mass famine event, simply because our food chain is now tied to a fragile industrial system.
So the lesson isn't just that the sun is powerful, it's that our own interconnectedness has become our greatest vulnerability. Okay, so we've established how bad Carrington was and how devastating a repeat would be. But we have to ask, was that the worst the sun can do? Or is there an even bigger monster lurking in the historical record?
That is the right question. Carrington is the worst storm in our recorded instrument-based history. But to see the full picture, we have to look further back, using proxy data from before the 19th century.
Let's talk about those deep time signatures. How can we possibly find evidence of a solar storm from, say, 1,000 years ago?
We look for specific radioactive isotopes that act as bookmarks in the atmosphere. When a truly massive solar particle event hits Earth, it creates these isotopes, and they get trapped and preserved in natural archives.
And the two main archives are tree rings and ice cores.
Exactly. We look for spikes in carbon-14 in ancient tree rings and beryllium-10 in ice cores. A tree ring captures a snapshot of the atmosphere each year, so it gives us an astonishingly precise timeline.
And when scientists looked at this deep data, they found events that make Carrington look small.
They did. They found signatures for what we now call superstorms. There was a massive one in 774-775 CE and another big one in 993-994 CE.
Let's focus on that 775 CE event. How does that compare to the storm that was setting telegraph poles on fire?
The carbon-14 levels from that event suggest it was about 20 times the normal background variation from the sun. And when you compare it to Carrington, it's estimated to be at least 10 times larger.
10 times larger. What would an event of that magnitude even do to us today?
I mean, it's hard to comprehend. It implies a level of geomagnetic power so far beyond what our grid was built for. The rate of change in the magnetic field would be so fast that any defenses we have would likely be saturated instantly. It could mean near universal transformer failure across the entire sun-facing side of the planet.
And there are hints of even older, even bigger events.
That's right. The proxy data suggests there might have been an even larger event way back in 7176 BCE. The record is constantly showing us that the absolute extremes are way beyond what we've seen in the modern era.
Now, we should inject a note of scientific caution here, right? Especially about some of the early ice core data.
Yes, that's crucial. Early on, some researchers thought that spikes in nitrates in the ice cores were a sign of solar events. The idea was that solar particles would create nitrates in the atmosphere that would then get trapped in the snow.
But that hypothesis didn't quite hold up, did it?
Not entirely. More recent analysis has cast a lot of doubt on it. It seems most of those nitrate spikes are actually from big terrestrial events, like massive forest fires.
And the proof is that the timing doesn't match up globally.
Precisely. If it was a solar event, you'd see the spike in both Greenland and Antarctic ice cores at the same time. But they don't align. So that tells us it was probably a local cause. We have to rely on the more robust proxies like carbon-14.
Speaking of refining the data, let's circle back to Carrington one last time, because recent analysis suggests even that event was more intense than we thought.
This is a brand new finding from 2024. Researchers digitized old magnetogram readings from London, and they looked at the rate of change in the magnetic field. That's the key factor that kills transformers.
And what did they find?
They found field change rates of over 700 nanoteslas per minute. Now, to put that in perspective, our modern grid protections are often designed for a 1 in 100-year storm, which is defined as around 350 to 400 nanoteslas per minute.
So the Carrington event was actually twice as fast and twice as powerful as our current definition of an extreme storm.
Exactly. The historical data shows that we've actually been understating its power. If a 700-plus nanotesla per minute event hit today, the stress on our grid would be exponentially higher than what we've planned for.
So after all of that, what does this mean for you, the listener? We've gone from a discovery on the sun in 1859 through these incredible historical stories to a potential $3 trillion disaster today.
I think the key takeaways are really clear. The Carrington event was this terrifyingly efficient storm. It was born from the first flare we ever saw and then amplified by that cleared fast lane that let it hit us in under 18 hours. It proved the universe can be beautiful and crippling at the exact same time.
And today, a repeat wouldn't just be a tech crisis. It's an existential threat to the hyper-connected systems that support everything: commerce, finance, even food. We just have so much more to lose now.
And understanding that vulnerability is everything. The knowledge we get from the past, from those 19th century operators and from the deep geological record, that's our best defense. It tells us we need better monitoring, better forecasting, and we need to harden our infrastructure against the true intensity of what the sun can throw at us.
All right. And for that provocative final thought we always like to leave you with, we've talked about the power of Carrington and these even bigger ancient superstorms. But the truth is, the physics of how solar flares generate this much energy isn't totally clear, especially when you compare our sun to other stars out there that produce superflares far, far larger.
And that leaves us with the ultimate question. Is our sun somehow limited? Or is it truly capable of unleashing a storm, say 10 times bigger than Carrington, that could effectively take modern global civilization offline, maybe for a generation? The historical record suggests the latter is entirely possible, and that forces us to consider the ultimate terrifying fragility of our modern connected world.